Hello. I think my microphone is working now. The author would like to express his appreciation to Mrs. Helena Russo, Mrs. Janet Palome, and Mrs. Betty Birdsall, who did the lengthy and frequently very difficult typing of the manuscript of this book. Poughkeepsie, New York, January 1980. The public committee process, the very first part, was standardization of character sets, of course. The standards process, very important. Terms and concepts. Binary variables, bits. We're getting down to the basics. Character sets. Whole patterns. It is common practice in punched card applications to punch the 11 punch in the same card column as a numeric to indicate a negative numeric. Thus, 11-0, 11-1 through 11-9 represent -0, -1 through -9, respectively. Yep. Redundant encodings. Complexities of using 8-bit character sets. You couldn't fit, no, not 8-bit, whatever, 6-bit, no, 7-bit character sets, so that the Swedish chef letters are different between countries. BCDIC whole patterns. A bonus post-it. There's something here about collapse logic I don't quite understand. But I might have to do with considerations for printers, considering you're just changing out a printing carriage, but you're not necessarily mapping characters to the same spot in the character set. Early codes. Now it gets interesting. We have CCITT number 2, field data, BCDIC, the predecessor to EBCDIC, the stretch code used in the IBM 7030, IPC in the Air Force, 64-bit character code by H.S. Bright, a 256 character code by R.W. Beamer, and a 4 out of 8 code table of characteristics. So CCITT number 2 is a shifted code. So I assume that means like it has a character mode and a figures mode, and so the same bit pattern can represent figures or characters depending on the mode that your printer state machine is in. And they're in a non-contiguous sequence, probably because they were ordered due to some characteristic, like they were most common. It was about typing frequency, either for something to do with keyboards or maybe for electrical characteristics. So CCITT, the telegraph, what telegrams were sent on, I suppose, is significantly different from all the other ones. The other ones all seem more modern in that they're not shifted. Like BCDIC is non-contiguous sequences. So do the Bright and Beamer proposals, whatever those are. Field data. Developed by the United States Army for use on military data communications lines. "64 code positions defined." An interesting special character. Not really. Spec is special. And stop and idle. Master space, uppercase, lowercase, line feed, carriage return. So, field data is also, well, this doesn't call it a shifted code. So I don't know what that means then, other than numerics are in the same sequence, but if it has an uppercase and lowercase, it must have a state. Assuming these mean transition to that state, or maybe no. Seems like a state machine to me. So BCDIC came from the punch card code. Around 1932, they started adding 26 letters and 3 symbols: A through Z, minus sign, asterisk, and ampersand. We have one interesting character, that the lozenge. Because the lozenge appeared on printer chains, it was put to various uses. We had it because we had it on printers for some reason. This is about the IBM Stretch. An 8-bit architecture machine with 256 character code. Possibility, though they only had 120 character set. 120 character set. It should contain enough mathematical and logical symbols to satisfy the needs of programming languages such as LWAL. Satisfying the needs of LWAL. The binary sequence of the bit patterns should match whatever collating sequence was prescribed for the graphics. And here's where you start to get into impossibilities, I suppose. Getting universal character set, because ultimately, if you choose the starting basis of the 26 characters in Latin, modern Latin, whatever you call it, and then you have different languages with different collations, you start to have problems. I don't know if that occurs exactly with the 26 character set, but you think about Turkish and the dotless I, for any language that inserts more letters into that sequence, it doesn't put them at the end like whatever Swedish or some languages do. They're not going to be able to satisfy the criterion 5. The Stretch 89 character set had subscript numerals in the 120 character set, which also had things like lozenge, down arrow, whatever, I don't know what that is. With down arrow, up arrow, or, and, not, or. Some punched cards. The special characters. In IPC, the Information Processing Code, developed by Edward Moranoff, John B. McLean, and Lieutenant Lawrence Odell in 1964. It was an 8-bit code, however only 128 characters were specified. Some fun special characters. Phi, Kappa. Certain fraternities and sororities were not very happy about this inclusion. Cubed and squared. All 4 arrows. Similar to extended ASCII, but I don't think all of those are in extended ASCII. 8859.1. An early 64-character code proposal by H.S. Bright. I wonder if he's related to Walter Bright. Structurally compatible with BCDIC, but so that the alphabetics are in relative collating sequence. An early 256 character card code proposal by R.W. Beamer. Talking about graphic to whole pattern relationships. And supporting the Algol characters. And characters used by other manufacturers should be included. And there should be a simple relationship between upper and lowercase alphabetic whole patterns. Some Algol words were arbitrarily assigned to simple graphics. If is assigned a question mark, begin to open curly brace, and to close curly brace, an integer to pound. Semi-arbitrarily, I would say. Also, comment to double quote, stop to bang, and return could be assigned to left arrow. Record mark and group mark, which sort of look like not equals and not that was congruent to exactly equals or something. There was another code that was a 4 out of 8 code that had a certain amount of error correction or detection built in. So it was an 8-bit code that allowed 70 patterns with 64 graphic characters or data characters and 6 control characters, which fit with BCDIC. So it's kind of like a line encoding. The Duels of BCDIC, Chapter 4. So, we start by talking about IBM chain printers from the 1950s. And they had lozenge on them, which I do seem to remember occasionally seeing on things that were printed on big computers, like standardized tests before they came on laser were on probably these chain printers, and I feel like sometimes they use that character like in our test score results or something. And here we start talking about European language requirements. So they increase the character capability from 48 to 51, which slows down chain printers because there's more characters on the chain. Save space, it was observed that 3 special graphics were peculiar in origin and use to English-speaking countries. Therefore, they were never needed nor used at that time in continental European countries. So, just say no, 9, no to the at, the octothorpe, and the $sign. Fortran requirements. So apparently, one sort of BCDIC mojibaki would be if your German had its A's, A umlauts, turn into octothorpes, hash marks, pound signs, or your AE letters in Norway and Denmark. That could happen because you didn't have a very big character set. And here's some Fortran mojibaki. equals is pound. Yeesh. Yeah, they're not even symmetrical. Open parent is percent and closed parent is lozenge. Star is star. Yeah, that looks awkward. But I'm sure you got used to it. And then version 3 of BCDIC came along. The size of BCDIC. I'm sure there's a joke here, but I can't even come up with that. What limits the size of the character set? It's the number of characters in the character set. It's a very philosophical question. Notation is mathematical. Once the binary aspect of the physical medium is perceived, the binary capacity must next be determined. Some examples follow. More boring IBM specific stuff about hole patterns. Final version of BCDIC on the 1410. PTTC. This is a new one. In 1959, engineers had started to design and develop new communications terminal, which came to be the IBM 1050. Book really hammers permutations. Like, yes, this is your numbering space. These are how many things you can fit in your numbering space. Thank you. Yes, we can do that calculation. Thank you. So PTTC, I wonder if this was used on the IBM MTST. So they're talking about two different modes. Either talking to another 1050 terminal or talking to a computer. In the first two modes, both lowercase and uppercase capability would be used, but in the third mode, data entry to a computer, it was assumed that only uppercase letters would be used. This is because the printer of the computer had capital letters only. And The fewer times an operator has to depress the case shift key, the higher the operator productivity. Productivity. Some more exciting characters in PTTC version 5. Delta or something. Lozenge. I'm not sure what they're saying with plus and. /B. Don't know what that's used for. Radical, gamma. Some more of those strike through symbols, maybe. I don't know. I think there's just typographic marks. I don't know what that would be. The structure of EBCDIC. At least one new data processing application, a text processing application, allowed a customer to order a special IBM 1403 print chain to allow him to manipulate and process upper and lower case alphabetic. So text processing in the era of the IBM 1403. Which was introduced in 1959 and had an exceptionally long life, according to Wikipedia. It was seen in Dr. Strangelove. It's unclear exactly when the text processing application was happening. There's a movie with some text processing. Was it 3 Days of the Condor? I think that they show some, whatever, 1970-ish computerized text processing, or hint at it. I don't know if they show any actual computers. This is it, folks. The makings of EBCDIC. Thrilling. Here it is, 5 decisions made in order to exhibit and reference the EBCDIC code table. 8 bits, numbered 0 to 7, in a 16 by 16 grid, referenced with hexadecimal numbers, by column then row. The code table will be divided into 4 quadrants, and in order to exhibit the card code, the code table would be shown in 4 unequal blocks. Whatever that is. The Duels of EBCDIC. I probably should have read the bit about the dual pairs in BCDIC more, but we'll probably find out more in Chapter 9, The Duels of EBCDIC. The two defects of BCDIC were duals and collating sequence. The BCD collating sequence is arranged in this lovely bit pattern where we have the numbers, the last third of the alphabet, the middle third of the alphabet, the first third of the alphabet, and each of those groups is padded out by special characters. So you can't collate by bit pattern, only by those shorter sequences. Talking about the hardware comparators in IBM machines, only certain machines. If you had the right hardware, you had a compare instruction that first performed the equivalent of the convert instruction. So that the hardware would, they fixed it in hardware because it's IBM. You have the choice between a performance penalty or a hardware cost penalty. And thus EBCDIC came about. The primary design factor of EBCDIC was that the BCDIC collating sequence could be embedded in EBCDIC by rearranging the blocks. And so we can see in the bottom right here sort of this diagonal arrangement where part of the bit sequence becomes significant in a different way, I think. I don't know. It's Friday night. I'm not going to figure this out, but it seems like it's probably very clever. Because you have the last block, which should go first. No, the last block with A should go first. So we've put it here, which collates, importantly, in the 1-0 part of this bit pattern, which comes before the 1-1 part. And then the rest of the alphabet comes later. So we have 4-3, so this is the middle third of the alphabet, the last third of the alphabet. And so we have 5 rows in each of these. And if you ignore part of the bit pattern, then you have an interesting thing here, I think, where this part is going to move through the alphabet cleanly, and so I suppose then you just need to look at these plus the last digit here to differentiate letters, to collate letters. At least those bits for a single case alphabet. Fascinating stuff. It's time for a drink. All right, I'm back. So, technical decisions about EBCDIC. Exciting stuff. Look at this. It would be 64 control character code positions and 192 graphic character code positions. I think that corresponds to whatever ASCII character set included the high control codes, but ASCII, regular ASCII, only has 32. Well, regular ASCII only has 7 bits. But I can't remember the IBM. The IBM PC had printable characters for every position, but some of them were also control characters. But I can't remember if the C1 control codes in the 7-bit high 128 and up character set, there was a second set control codes there. I'm not sure if those were part of the PC standard or not. It was decided intuitively that lowercase alphabetics as well as uppercase alphabetics should collate low to numerics. I wonder what the intuition is there. Numerics seem more primitive to me. Don't know. A bit about the magic that is the EBCDIC blocks, why they live where they do. We can see the EBCDIC to BCD relationship here. More whole patterns. So much of this stuff really affected by engineering constraints, physical things. So in BCDIC, we had the same character. We had different characters represented by the same bit pattern, depending on whether you had commercial graphics or scientific graphics. So you could have the A chain or the H chain. And so the question was, in EBCDIC, should the same bit pattern represent percent or open paren? Let's find out. We have a few choices about retaining whole patterns. Including retaining all of them for the A duals, or all of them for the H duals, or for some of each, or assign new whole patterns to all of them. So what did IBM decide to do with the whole patterns? Oh my god, this is possibly the dullest thing I've ever read. It's fascinating. IBM's decisions about whether or not to assign H duals or A duals to the historical position, or to not be backwards compatible with BCDIC. Because if you were using an EBCDIC machine and it wrote H duals in one position and you passed it to a BCDIC position, if it wasn't in the old position, it wouldn't get transferred. Or I don't know how it collapses things. Well, and that's the question. So there were vastly more tapes containing application data with A duals than with H duals, so maybe you just gotta recode all your H dual tapes. In the end, the 5 H duals were not assigned to any of the code positions. They were graphics used in programming languages. This is making my head hurt. They couldn't get rid of semicolon because it was a required graphic in COBOL. But they could get rid of less than and greater than because the COBOL spec said you could use GT and LT instead. On not much more than a toss of a coin basis, it was decided to replace colon by single quote. And then we have to talk about PL1, which I always want to call PLI, but I think it's PL1. Maybe it's PLI, but I'm going to call it PL1. There are 20 syntactics and 3 alphabetic extenders in PLI. I wonder if an alphabetic extender is like underscore, tends to be these days in most languages. $sign is in JavaScript. And here we see the not symbol, which was in early ASCII, like ASCII 63, but not ASCII 69 or something like that. No EBCDIC graphic would be assigned to replace the BCDIC not equals, or just single line striking for 2 lines. I don't know. Oh, the alphabetic extenders. There were 3, so that German and Swedish and Finnish and so on had a few extra characters. The BCDIC specials in EBCDIC. So there are 2 in some of these spots. So are these? I don't know. So EBCDIC didn't have the square brackets, but BCDIC did. So are these duals then? Are these the duals of EBCDIC? A question that arose was whether the collating sequence had been affected by these changes, the final assignment of specials. The primary criterion in the development of EBCDIC was that the collating sequence of BCDIC should be embedded in the EBCDIC collating sequence. In a very real sense, this criterion had not been aborted, even though many BCDIC graphics ended up with card hole patterns different than their BCDIC card hole patterns. Tough decisions had to be made. Oh, the duals. Yes, look at all of these. Look, plus, where does it go? What a question. Oh, the consequences of reassignment. Backwards compatibility, everybody. You make one decision on your printer chain in the 1940s, and somehow, decades later, you're still building mainframes that have character sets that have been affected by the decisions of whoever put together that printer chain. The graphic subsets of EBCDIC. Here we see the keyboard of the 029 key punch. The 88 key subset. Now this, I think, is the subset that you can find on ASCII keyboards. It's, well, roughly like the original Apple II, no letters after it. I think had roughly this keyboard. Did it have not? I can't remember. But it was close to that. I think maybe that one had up arrow or something instead. But so I think, yeah, the sort of ASCII keyboards of the 1970s are pretty close, though they don't have cent. But yeah, they were similar subsets anyway. Typewriters at the time had cent too, but that, I think cent got dropped from ASCII between 63 and 69 or whatever. Here we see our old friend Lozenge. We have a character set that includes closed curly brace, but not open curly brace, just for fun. So ASCII, the US 7-bit code, has 94 graphics. Except, yes, we have the square brackets in ASCII that aren't in EBCDIC, and EBCDIC has sent and not. Oh. And then pipe is arguably different, I think, depending on whether it's broken bar or not. Vertical line, they call it here. I don't know whether you consider that the same character or not as the modern character set. Now we talk about chain printers. The size of a chain. So a chain printer might have the character set 5 times on it. It doesn't have to spin all the way around, or, well, it doesn't quite make sense. However, somehow they have a big mechanism with letters multiple times. It doesn't sound like the frequency coding, it's just I don't know. Anyway, they repeat the 48 graphic set 5 times, or a 60 graphic set 4 times on a 240 character chain. But a more subtle method is to repeat more frequently used graphics more often than less frequently used graphics. And then we get into subsets for PL1 and for katakana. And katakana was originally assigned in EBCDIC as 47 graphics, which we see here. Katakana 47. We shall learn in Chapter 18 that the assignment of katakana and EBCDIC created complications. The card code of EBCDIC. More boring IBM engineering specific stuff, blah blah blah. We made these decisions about our machines, so they affected our character set. Things happen. All right, so the new PTTC for the IBM 1050, the punch tape terminal code, which became PTTC6 and PTTC8. Eventually those were renamed PTTC BCD and PTTC EBCD, corresponding to PTTC for BCDIC and PTTC for EBCDIC. Some more thrilling decisions about mapping character sets for the IBM 1050. The alphabetic extenders for European and South American countries. Whole pattern displacements, which led to musical chairs. Oh, the trials and tribulations of being a character set designer for PTTC BCD. God, this is dull. The dual case set. So these are mode characters, and that's a hair. So duo case means yes, we have a mode here. So I'm not sure what that table that we looked at earlier was trying to say, because yeah, some of these definitely have modes. There's an uppercase mode, a lowercase mode. And then we get to talk about check bits. As has been pointed out, there were a number of differences between PTTC BCD and PTTC EBCD. These stemmed mainly from changes going from BCDIC to EBCDIC and from different principles for assignment of card hole patterns to the small and capital alphabetics. Before the design of either PTTC, the well-established hole patterns for alphabetics had been assigned to capital letters, the only kind of letters then available on monocase data processing equipment. The use of a duocase electric typewriter for PTTC BCD and for PTTC EBCD introduced the capability for both small and capital letters. The principles established for PTTC BCD and for PTTC EBCD were as follows. PTTC BCD. The card hole patterns previously associated with monocase alphabetics will be assigned to lowercase shift of the typewriter, regardless of whether small or capitals appear in that case shift. On PTTC EBCD, the card hole patterns previously associated with monocase alphabetics will be assigned to capital letters, regardless of whether capital letters appear in upper or lowercase shift. The principle for PTTC BCD had as its objective maximum simplicity of the logic circuitry between the keys of the keyboard and the hole patterns of the punched card. The principle for PTTC EBCD had as its objective unvarying for the future hole patterns for small and capital letters, even though this would increase the complexity of logic circuitry between the keys of the keyboard and the hole patterns of the punched card. So, IBM created a simpler character set to simplify the electronics required in the electronic quote-unquote typewriter, the teletype terminal. Next up, the size and structure of ASCII. However, I'm going to leave it for another day because EBCDIC is absolutely exhausting. Anybody who's watching this, thank you. And I'll be back soon, probably.